So now we come to PFC, right? What have we got? We got these bonded, we got these particles here, we got these bonded things, and what we really have is assemblies of these particles. There's three types of fundamental particles, either disks or spheres in 2D and 3D. We can have overlapping collections of disks and spheres, which we call a clump. A clump behaves as a rigid body with just a weird shape made up of this bumpy set of spheres that overlap. And then we also now have what we call rigid blocks, which are general polyhedra. These are the fundamental particles that can then interact and move around and be glued together that we support in PFC. Again, what we really do here, the main people that are using PFC are using it to do basically rock mechanics type research, where what we really do is we're creating a synthetic material. Any PFC model where you bond these things together could in principle be constructed in the physical world, which is really interesting. If you have a constitutive model in a continuum code, that particular material that's a complete mathematical continuum mechanics idealization with plasticity theory. You could not directly physically construct such a material in the real world. But when you have these particles of these well-defined shapes, you could, in principle, take those things, put those particles together. If you had the ability to control the properties of the glue, you could in fact build such systems, right? And then you could load them and you could look and you could see what they're doing. That's what we do with PFC. And anything that you could learn from building such systems, and building such systems in many ways is an example, is sort of like a sandbox model to some degree. And so we think of PFC as constructing a synthetic material. And then of course people look at bulk flow, mixing processes, in a mixer, and you've got dough with chocolate chip cookies, and you're putting in the chocolate chips, and you're moving this thing around this mixer, and you want to say, how do they get mixed, right? That's the kind of thing people could look at with PFC. And of course, what we're interested in is this idea of gluing these together to make solid bodies. And then we're going to look at the bond breaks, which is going to be the damage, which are going to be thought of as micro cracks. Okay. Here's the basic idea again. We've got these rigid bodies that can move around, and these rigid bodies come into contact with other rigid bodies, and at that contact there's then going to be a force that develops, and it's going to be equal and opposite and act on those two bodies. And so we then can model that type of system using this numerical technique called the distinct element method. And basically what we're doing is taking small steps forward in time, and we're constantly updating the positions of these particles. And then when they come in contact, we're saying there's a contact there, we're storing a force there. We're basically using Newton's law, F equals ma, to figure out the motion of this system. And we'll talk about this quite a bit when we get into the physics. Again, the basic particles here is we have the disk or spheres. We can also have these convex blocks, and then we also can clump these things together. All right, so here's an example of a PFC model of a drift. So this is a 2D model. This is the face of an advancing drift in a gold mine in South Africa, deep underground, about 3 kilometers. It's quartzite, it's extremely high stress. And as you advance this thing, you're advancing from left to right. You're basically just deleting particles, which represents an advancement. And here at this particular stage, these are all the broken bonds. Red is micro tensile failure, blue is micro shear failure, and one of the things you're seeing here is a shear band forming along here and a shear band forming along here. As you move this forward, the stresses are so high, it like pushes material in behind the face. Of course, this shear band here now is actually, you could go into detail if you really want to understand the behavior of a shear band and look at, oh, that's made up again of all kinds of complicated collections of broken pieces with these shear and tensile failures along the way. Here's an example of a PFC3D model of boulders, and it's a rock slide coming down a slope. We're going to look at this later and watch this thing roll down the slope. These are clumps. If you look inside, you can kind of see there's a whole bunch of spheres that are all overlapped to represent a single rigid body. And so these things then are just bouncing down the hillside, and people look at what's the final distribution of boulders. If a rock slide were to occur, what kind of damage might they do? Here's an example of mixing. This is a rotary kiln. This is a PFC3D model. These are actually rigid blocks. They look kind of like 3-to-1 aspect ratio blocky material. This is some kind of clinkers in some kind of rotary kiln. There's also temperature in here. They're heating this thing and they're mixing it, and it keeps on falling back down. We'll see an animation of that in a moment. Here is the key picture that describes bonded particle modeling here. What this is a collection of little 2D little discs that are yellow. They're packed arbitrarily. There's about 100 of them by 100 of them. And then these holes are drilled into it. Again, this was for the Yucca Mountain project. And what we're looking at here is we're squeezing it between these two rigid surfaces. Think of this as an enormous UCS test. The scale here is 1 meter by 1 meter. As we squeeze that, we can look at the forces pushing against the platen. If we sum up those forces and divide by the cross-sectional area, we're going to say that's the axial stress. We're going to plot that on the y-axis. Then we're going to look at the motion that we're imposing and the change in the change in distance over the length. We're going to call that the strain. And so we're going to plot stress versus strain. We're just measuring that. What we're going to also see here is when we squeeze this, the forces have to flow. If I squeeze on the top, the forces have to flow through the material to get to the bottom so that the whole thing remains in equilibrium. The way that forces flow through a granular system is by means of these things we call force chains. And basically, it's like a network of force. So blue here is compression between the discs, and they're getting pushed, and these force chains are indicating how that load is flowing through the system. There's also cement in here, what we're typically call a bond. And what we're going to find out is when you squeeze a granular system that's bonded, you're going to compress it this way. You're going to cause tension in this direction. So black is compression in the cement. Red is tension in the cement. This induced tension is the thing that breaks the bonds. This is also the fundamental reason why rock will break. It's how it responds to stress. If it's compressed, you generate all these microtensions inside the rock, which then cause it to fail eventually by linking up. So the magnitude of these forces is related to the thickness of these things. Okay, and in a minute I'm going to run this. We're going to see the animation of this, but I want to point out a bunch of things first. So by squeezing this, there's a whole bunch of tension above the hole and below the hole. That's what happens because of the elastic response. Remarkably, if you glue together an isotropic packed set of discs or spheres, and if you just put infinite strength on the glue and you exercise this and apply all sorts of deformation to it, lo and behold, it will behave like a linear elastic isotropic body. Okay. But then of course, what's also interesting, it will begin to fragment and break just like a rock will break. And so of course, its properties will change as that happens. So let's just watch what's going to happen here. As we're starting to load the specimen, and these are constantly scaled to the same thing. So there's little load in here right now, but we're beginning to pick up load. That's the stress and the strain. Now just watch as this thing gets loaded more and more. It's going to start to fracture, and the load's going to start to get redistributed. Watch over here. There's going to be a fracture forming. Now this is compliant. It's not carrying load anymore. And eventually the whole thing breaks. Here's the stress strain curve. Goes up, and it's eventually coming back down to zero. This is not a brittle fracture. If I had a bonded assembly that didn't have the holes in it, it would be much more brittle. Because of these holes, you're getting the ability for load to be redistributed quite a bit. And this thing is failing from the outside in. I show this to mining guys and they say, oh my God, it's like a pillar in a mine. It fails from the outside in. See, there's still confinement from this material on this region here. That's why it's still carrying load. Of course, that loads eventually. You can see a giant fracture that's formed up here. Okay. We're going to talk a whole bunch about this in day 3. We spend the whole entire day talking about bonded particle modeling, and we're going to look at this thing in greater detail. But I could give a 5-hour lecture about the fundamentals of rock mechanics by talking about the micromechanics of this type of model. So that's a precursor of what we're going to be talking about. Here's another example of what people do with PFC. They look at material flow. This is a caving situation, and you say, we got all this broken material, we put colors in the different layers, and now we start drawing material just from this draw point. And so you can see the region of mobilized motion because of that, right? This flow pattern is going to be highly sensitive to the shapes of the particles, to the size distribution of the particles, to the friction on the surface of the particles, and etc. So people use this for example, for caving. It was one of the big sponsors of the initial PFC was a consortium of caving companies that wanted to model caving. The idea was, could you do that with PFC? There's particle flow. Here again this is a deep gold mine in South Africa, and this is a notch that is formed. This is quartzite super hard rock. It's got a UCS of almost 300 MPa. This is very high stresses horizontally, very high stresses vertically, and this is a notch that's formed in the excavation. You can see how sharp it is, and you can see how big it is. You also see how horrible it is to work deep underground in a South African gold mine. This guy's sweating. It's like super hot and humid. When you're down at 3 kilometers, the rock itself is much, much hotter than on the surface. So they have to do all kinds of cooling so that people can be down there. It gets very humid. This is that model we built of that situation. This is just a cartoon of the idea. Here's the advancing stope. It's a 2D model, so it's assumed to be very long in the out of plane direction. We basically have a continuum code that provides the boundary, far field boundary conditions, and then we go and put PFC in a local region in front of the stope, and then we carve out PFC as we go. There's this generalized coupling where we take the boundary of the PFC particles, we identify them with the colors, we then associate each one with the edge of a zone, and then what we basically do is we say the motion of those boundary value, those boundary points, those faces of those zones, that motion is imposed on the PFC assembly. Meanwhile, there's resulting compressive forces that the assembly generates. Those compressive forces are turned into tractions and imposed as a boundary condition on the face of the zones. And so we have a tight coupling between the two. This was done in 2012. This was all done with a bunch of fish functions that I had to write. Since that time, the ability to embed PFC material into a larger FLAC or FLAC3D model is built into the code. It's very straightforward, but it does the same sort of an idea. And this is just showing the behavior that we see out of that. Remember, this is the continuum. These, as we advance the stope, what happens is these big shear fractures form, this localization of deformation. And here we're showing it's beginning to form right there. You can see it's cleanly going from the bonded thing into the grid. We're not getting any distortion at the coupling boundary. As we keep going forward, here's another shear fracture that's beginning to form. And of course, we can look in detail at the detailed physics of what's happening in a shear fracture. There are people who use PFC to do that type of work as well. The one interesting thing, I'm not showing the whole 19 meters, but what happens is these shear fractures keep forming as you advance, and then because you have a big unsupported span that starts bending down, and you get these tensile fractures that form above it. And so we're seeing both of those things in the models. Some of them in the continuum, some of them in the shear part in just this PFC region. This is what they see underground as well. Seems to be making a lot of sense. All kinds of other applications, just quickly showing you. Here's a rock cutter that's rolled against the surface with very high normal force. Here's a borehole breakout type of a scenario that's modeled with all these little particles. Here's a rock blasting thing. This is a bench. They drill holes in here. You pack it with explosives, as you probably know. You blow those up, and then you break out the face of this bench, right? So here we're looking down on one of those blast holes, and here's the damage that is getting produced as a result of that. Let me show you another example. This is some work I did to look at rock cutting. This is what they call a polycrystalline diamond bit. You can see the scale. It's like 13, 14 millimeters across. It looks like a little watch battery. It has on it this synthetic diamond. That's what the black is. This is some kind of metal. This is the diamond because you can make a really sharp edge on that thing. This is then pressed against the surface of the rock and dragged across the surface of the rock as part of a larger bit. And that's what's used to do the cutting. So we can build a PFC2D model of that system. This is the synthetic sandstone. You can see it's got about 240 grains across. This is just held in place. These are what we call PFC walls. They're just surfaces then that can interact with the particles. These guys started over here and have been moved at a fixed depth of cut, and you can see the brittle nature of the damage that's forming. What you do in this thing is you're monitoring the total force, the forces, because you know the forces all along the face of these cutters. And what you're doing is monitoring force versus displacement. You can turn that into energy to cut. So this is an example of what they call a dry cutting test. This would be like sitting on the surface, and in a laboratory, you can drag these things and basically scratch out the surface and measure energy to cut. Turns out that at the bottom of a borehole, there's all this drilling mud, because you got to have a way to flush out the cutting. So you have a big drill pipe, which is hollow in the middle, and you pump water down the middle, and the borehole has a bigger diameter than the diameter of the pipe. So you pump water down the middle, it picks up cuttings and it flows up the outside of the pipe. It also, though, unfortunately provides confinement to the surface of the rock. Turns out that it takes like 10 times more energy to cut an equivalent volume of rock if it's at the bottom of a borehole with that drilling mud than it does on the surface. So these surface tests are only a little bit worthwhile, and it's very difficult, if not impossible, to see the cutting process where you have all that drilling mud and stuff. Although people have tried. I used to work with Hughes Christensen. They developed this work a while ago, and they have a big giant facility down in Houston where they actually have a big huge tank and have drilling mud, and they're like doing all these experiments, dragging these things along. But they still, at least at the time, about 10 years ago, had not figured out how to actually see the cutting process as it was going on. One of the things the guy did is pounded in nails to these surfaces, and then he would run the test and he would look at how much these guys had bent to try to get some idea of the forces. So to incorporate the effect of drilling mud, what we did is I applied a boundary condition so that on the surface we could have like a membrane, if you will, that presses down. When we then run the exact same model with that boundary condition, we get something that looks like this. Notice so black is the existing cement, yellow are just the particles themselves. And what we get here, of course, is because there's confinement on that surface, these chips that want to form are suppressed. And instead you basically build up these like, looks like a snowplow, this like broken material that works its way up the faces of the cutters. You also see in here that the cutters are never in contact with the virgin rock. They're always in contact with broken bits of rock that then is pushing against this. This is what actually they believe really happens in cutters, and this is why they believe that tiny changes to the geometry of the chamfer have giant effects on energy to cut. When I actually did this initial work back in like early 2000s for this guy at Hughes Christensen, and what he did is ran a bunch of these models and just looked at animations, and he then suddenly was like, oh my God, you got broken material. This is material flow. This is frictional granular material. It's flowing around the boundary bottom here. That's why the shape of this has such a big impact. And so that was an interesting thing. It's one of those things where like you have a model and then you see things with it that you wouldn't have necessarily thought of to begin with. And we'll talk more about this rock cutting. that's a good example. Here is looking at flow through a ore pass, right? You guys both know what an ore pass is. This was actually a real problem that was looked at because they were getting uneven flow from here, and so they redesigned the orientation of this, and they did all this with PFC3D. And this is just a cross section through that 3D model, looking at the mixing and where things are going. Here's a screw conveyor, right? I actually go deer hunting in southern Minnesota with a bunch of farmers, and they all have corn in their big silos, and they have a screw conveyor. That's how they get the corn out of their silos. It's quite fun. I hunt with all these people. Many of them barely finished high school. They're super hardworking people. They're farmers, and then occasionally they ask me though, so what do you do for a living? And so I talk a little bit about, I do computer modeling of how your silo thing works. So this is the kind of thing you do with discrete elements. Here's conveying. These scoopers are bringing this material up and flinging it out. Here is that rotary kiln. These are PFC3D rigid blocks, and you can see how these little scooper things here are kind of helping to lift this. You can see they're picked up there, they're dumping. This, by the way, is called a dynamic angle of repose. This is a higher angle than if you just had a static system of a sand pile. But this is the kind of stuff you can do with PFC3D. There's other things that people have done that you can put in magnetic forces acting on the system. You do that with a bunch of fish functions. This is looking at a grinder, coffee beans, and now we're going to just look at a few examples. Now, just think this music, da, 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 it's going on as you're watching this. Those are coffee beans modeled as clumps thrown into that thing. Here's again some material flow through these bins, flowing through there, looking at the process of what's going on. A lot of people use these type of approaches for materials handling. This is a very cool one. What are we looking at here? What we're looking at is deep underground. This is a backfilled panel, 15 meters across, very far in the out of plane direction. And what they've done is they've backfilled this, and then they've opened up, they've carved out a 15-meter chunk here. And there, in this case, it wasn't strong enough, and the whole entire roof of this thing collapsed. This was calibrated bonded material that was calibrated to have a UCS of 0.5 MPa. So 0.5 MPa in your rock fill is not enough to handle a 15-meter undercut. So then they went and they made a, whoops. Oh, I'm going to look at this later. I don't have it in here. We'll look at this later. But then when they made the UCS 1 MPa, they were able to undercut it, and you've got broken material, and it formed a stable arch. We'll see that later. And this is a cyclone separator. So we've got fluid now interacting with the particles, and you can see them flying around in the air here and interacting with the sides of this thing. This is the example of coupling with a fluid dynamics code to provide the fluid flow field, which is then producing drag forces on the particles. Meanwhile, the particles are affecting the porosity in the cells of the fluid model. This is an example of a disperse assembly of particles getting dragged along in a fluid. This would not be an example, obviously, of a poroelasticity thing. That's a whole different type of system. That's a dense packed system with these small pores that have fluid in them. So that has to be handled in a different way. The last couple of slides here talk about PFC has really often been used by researchers who are doing science. This is numbers of papers that were written about use of PFC to do various things. This is not cumulative. This is each year. So in 2020, about 220 papers appeared in the scientific literature that were using PFC and studying different things. Here's the different sort of journals. International Journal of Rock Mechanics and Mining Sciences obviously is a big one of how many papers we found in there. And just again, PFC, it comes from the original work that was done by Peter Kundal, and he wrote this paper in 1979. It's the most cited paper in the world of rock mechanics literature. Of course, it's most cited because it's the paper that everyone who ever does a paper about discrete elements always refers to this paper because it was the first one. Then we came along and we did this work to create this bonded particle material. And this has also been cited by many people because it was one of the first developments and uses of bonded particle type approaches. And so again, anybody who writes a paper about this type of stuff often refers to this 2004 paper. The kind of really nice, interesting thing about this begins its life as a solid material, and then it starts to have all these cracks. And as it breaks up, it eventually could become a granular material. And of course, most rock is in a stage somewhere in between this, right? And this is the last one I think is very pertinent to what we're talking about in the course here, right? The development of the bonded particle model represents one of the most significant contributions to modern rock mechanics research. And this last sentence, I think, sums it all up really well. It is now well established that this model has the ability to reproduce the essential and some more subtle features of the initiation and propagation of fracturing in both rocks and rock masses. That was written by Everett Hook and Derek Martin back in 2014. So this is not just fun in games and like pretty pictures. This is a proper defensible scientific model of the microstructure of rock.